The last few types of indeterminate form that we're going to talk about here end up as 1 to the infinity power, 0 to the 0 power, or infinity to the 0 power. 1 to the infinity power, I don't know if that's necessarily 1. 0 to the 0, 0 to any finite power is 0, but anything to the 0 power is 1. So is it 0 or is it 1 or is it something else? And then infinity to the 0 power, right? Any finite number to the 0 power is 1, but what about infinity to the 0 power? I don't necessarily know what that looks like. So if we're working with a function that looks like this, f of x raised to the g of x power, we're going to take this function, we're going to rewrite it in a very specific way. I'm going to rewrite, in particular, pay attention to f of x right here. I'm going to rewrite that f of x as e to the natural log of f of x power. Now, normally no sane person would write it that way, because if I were to write e to the natural log of f of x, remember the exponential e and natural log, these are inverse operations. They cancel each other out, so I would just be left with f of x. So I haven't actually changed what this expression is equal to. I've just chosen to write it in a very particular way. So, okay, I've chosen to write it in this way, and then I say, okay, if I look at the powers here, if I have a power raised to a power, I can then multiply those two powers. So I can rewrite that as e to the g of x times natural log of f of x. So the important part here is that this starting expression, right, that's what I'm looking at the limit of, I can rewrite as e to the g of x times natural log of f of x power. So if I want to look at the limit of f of x raised to the g of x power, I can look at the limit of e to the g of x times natural log of f of x power, or just look at the limit of that power since e is just a constant. So what I'm going to do here is I'm always going to be looking at that power, because when I rewrite that power as g of x times natural log of f of x, we should be able to rewrite that in a form that gives us 0 over 0 or infinity over infinity when we try to evaluate the limit directly. So here's our procedure here. If we're working with f of x raised to the g of x power and we end up with 1 to the infinity, 0 to the 0, or infinity to the 0 power, any of these three outcomes, we're gonna evaluate them all the same. We're just going to start by looking at the limit of this power. So the limit as x approaches a of g of x times natural log of x. Notice that's just this power right here. We're just looking at that power, and we're going to give that a name. How about we call that just L? This limit we should be able to put into the form 0 over 0 or infinity over infinity, and then we can use L'Hopital's rule. So we'll end up with a limit which we call L. And remember that this is just the power, right? This is just the power. So if I want to look at this limit, I can just look at e to the L, and then that is my limit. So let's look at an example here, because there's just kind of a lot going on. Here I'd like to look at this limit as x approaches 0 from the right-hand side. I have x raised to the x power. Now, if I tried to evaluate this right away, I would say, well, this is 0 to the 0 power, and oh boy, I'm stuck already. So I need to rewrite this in a very particular way. So I'm going to say, okay, this is now limit as x approaches 0 from the right-hand side. I'm going to write this as e to the natural log of x. So that's really all I'm doing is rewriting this part right here. That's just this piece. And then all of this is being raised to the x power. That's this x right here is being raised to the x power. And again, notice that e to the natural log of x, if I wanted to simplify that, it would just give me x. So I haven't actually changed the value of the expression. I've just changed the way it looks. So I'm going to rewrite this as limit as x approaches 0 from the right-hand side. If I have a power raised to a power, I can multiply those two powers. So I can say this is e to the x times natural log of x power. what I'm going to do is just look at the limit of this power here. So let's look at the limit as x approaches 0 from the right-hand side of x times natural log of x. Now, if we try to look at this limit right away, we'll end up with 0 times, if I look at natural log of x as x approaches 0 from the right, 0 times infinity, we have yet another indeterminate form, and, well, this one I can't use L'Hopital's rule with. But I'm going to use the same exact trick, and actually let's leave that there. I'm going to use the same exact trick we used earlier. Limit as x approaches 0 from the right-hand side. Rather than multiply by x, I am going to divide by its reciprocal. So I'm going to leave natural log of x in the numerator divided by 1 over x. So here, again, you can see that these two are equal. If you simplify this, multiplying by x, you would end up with exactly what we started with. So I've rewritten it in this very particular way, and now I'm going to look, okay, limit as x approaches 0 of natural log of x. We said that was infinity. Limit as x approaches 0 of 1 over x. That will also be infinity. And look at this, I have infinity over infinity. This I can now use L'Hopital's rule with. So let's go ahead and do that. So I want to look at limits as x approaches 0 from the right-hand side. Natural log of x, derivative of that, is 1 over x. 1 over x, maybe we'll just take a second. Remember, 1 over x, I can rewrite that as x to the minus 1. Perhaps that's easier for us to take the derivative of. So I'm going to write that as negative 1x raised to the negative 2 power. So, okay, let's just do a little bit more simplifying here. Oops. Limit as x approaches 0 from the right-hand side. This is 1 over x divided by negative 1 over x squared. So let's see, I can rewrite that. X approaches 0 from the right is 1 over x times negative x squared over 1. So, okay, what happens? I can cancel a power of x. Limit as x approaches 0 from the right, the only thing that remains is negative x. Limit as x approaches 0 from the right of negative x, I'm just going to plug in 0. Negative 0, well, that's just 0. So that's my answer, right? No, of course not. What were we looking at? Remember that this x natural log of x, the limit of 0 that we just found, that was just the power. So I just have one more step to take here. If I go back to my limit, kind of this original limit statement that I was working with, I say, hey, this power, I know that that approaches 0. E is a constant. We don't need to worry about E. That is always going to stay as 2.718, blah, blah, blah. But the power, that's what I care about. The power will approach 0. So e to the 0, I know that that will be 1. So this is my limit. E to the 0 power will approach 1. So there's a lot of steps going on here. We're kind of putting together all the pieces. We're rewriting this indeterminate form in a very particular way, and then rewriting even that power so that we can use L'Hopital's rule. So your algebra skills, they've really got to be on point in this section. Let's look at another example. This one's kind of neat. Here I have the limit as x approaches infinity. I have 1 plus 1 over x raised to the x power. So if I try to just evaluate this limit directly, I'd have 1 plus 1 over infinity. That should approach 0. Raised to the infinity power, I have 1 to the infinity power. This is an indeterminate form, but it's not an indeterminate form that I can use L'Hopital's rule with. So I'm going to rewrite this as limit as x approaches infinity. Let's see, this is e to the natural log of 1 plus 1 over x, put a parenthesis here, raised to the x power. Again, hopefully we see e to the natural log of 1 plus 1 over x. If we simplified that, we would just end up with 1 plus 1 over x, and then this power of x is just coming down right here. So I know that this 1 plus 1 over x raised to the x power is equal to e to the natural log of 1 plus 1 over x, and then that in turn raised to the x power. But I have a power raised to a power, so I'm going to multiply those two powers. This is really limit as x approaches infinity. This is e raised to the x times natural log of 1 plus 1 over x power. So I want to look at, I know e is a constant. I really want to look at what is this power doing. Let's see if we can't figure that out. So here, let's try to look at just that power. So we'll look at limit as x approaches infinity of x times natural log of 1 plus 1 over x. Now, if I try to evaluate this limit directly, I will end up with infinity times natural log, let's do this, times natural log of 1 plus 1 over x, as x approaches infinity, goes to 0. I have infinity times natural log of 1. This is infinity times 0. Infinity times 0, that's an indeterminate form, but it's still not an indeterminate form that I can use L'Hopital's rule with. So I need to use the same exact trick I used in the last example. I'm going to divide this natural log of 1 plus 1 over x by the reciprocal of x. If you need to, write that out. This is x over 1. So I'm going to rewrite that expression, limit as x approaches infinity, natural log of 1 plus 1 over x divided by the 1 over x. And again, we should hopefully be able to see dividing by the reciprocal, or rather, here in this case, if we were to multiply by the reciprocal of the denominator, we would have exactly what we started with. So let's try evaluating this limit. Let's see what we end up with. Natural log of 1 plus 0, 1 over x as x approaches infinity, that goes to 0. I have natural log of 1 over 0, 0 over 0. Yes, finally something that we can use L'Hopital's rule with. Again, you may want to take a moment just to remember, hey, 1 over x, this is really x to the minus 1 power. This is really x to the minus 1 power, just so that it's easier to take your derivative. So let's see. My numerator, limit as x approaches infinity, I am going to have to use the chain rule for this guy. So derivative of natural log of x, that should be 1 over 1 plus 1 over x, times the derivative of the inside part, that would be negative 1x raised to the negative 2 power, divided by in my denominator, negative 1x raised to the negative 2 power. And hey, look at this. I was worried I was going to have to do a little bit of simplifying, but I have a negative 1x to the minus 2 in the numerator, negative 1x to the minus 2 in the denominator. Those two cancel each other out. So let's look at this limit then. Let's see, 1 over 1 plus 1 over x. This will approach 0. I have 1 over 1. This approaches 1. But remember, that's not our answer. That's what the power approaches. We need to take this guy, right? This is all equal to L. You need to take this guy and say that is what this piece approaches. So my limit, e stays the same since it's a constant. E raised to, what does this power approach? Well, we just said it approached 1. So it approaches e to the first power, or just e. There is our limit. And this is actually kind of cool. This is actually a definition of e if you calculate this limit, and we actually just did. We calculated this limit using L'Hopital's rule and showed that if you look at the limit of that expression, that is where e comes from, or that is one of the definitions of e. So I think that's a very, very cool problem. Let's look at one more example. Here I have the limit as x approaches 0 from the right-hand side. I have x raised to the 1 over natural log of x power. All right, so if we try to evaluate this limit directly, I'll have 0. If I look at this power right here, and in particular natural log of x, I'll have 1 divided by natural log of x as x approaches 0 from the right-hand side. That's going to go to negative infinity, which 1 over infinity or 1 over negative infinity is just another way to say 0. So I have 0 to the 0 power. This is another indeterminate form. So all right, I need to rewrite this. This is going to be limit as x approaches 0 from the right-hand side, e to the natural log of x power to the 1 over natural log of x power. So this one's kind of interesting here. I have limit as x approaches 0 from the right-hand side. If I look at simplifying this, right, because I have a power raised to a power, here e to the 1 over natural log of x times natural log of x. Well, look at that. They're just going to cancel each other out. I have limit as x approaches 0 from the right-hand side, e to the first power. There's nothing else I need to do at this point. Because this is just a constant. I'm done. This is really just e. So, hey, that was a really nice unexpected result. I didn't even have to use L'Hopital's rule. I just had to think about how I could rewrite this in a very clever way. So, again, be careful. Make sure that you understand where this simplifying, or in air quotes simplifying, is coming from. We know that e to the natural log of x, that's really just another way to write x. So again, I've said it what feels like 100 times for this section. Please double check to make sure that you can use L'Hopital's rule before you actually apply it, because there are plenty of circumstances that we're going to see where L'Hopital's rule does not apply, and if you do try and use it, you'll get the wrong answer.